Welcome to our last part of activity 4. Today we're going to talk about compounding continuously. So what happens when we have a really big n, right? We have a really big number of compoundings. Well, what's happening is it ends up compounding continuously. And the formula for that is what we like to call PERT, and that's our final amount, initial amount, our rate of change, our time that we've been talking about before. And then this time, notice this little constant here, E. E is a mathematical constant whose value is approximately 2.7183. E is kind of like pi. It's an irrational number. It's just not as popular. So in our calculators, we have the pi button, right? We know we have pi right here, and our calculator has that stored in it. But our calculator also has E. If you do second division sign here, we see E. This is also another mathematical constant that's in our calculators. It's about 2.7182. You see the deal there. And again, your calculator has that stored in it. So when we are calculating, we have Brian, and he's investing a starting amount of $8,577 in an account with an R value of 2.89. So 0.0289 for our R as a decimal. And this time we are going to use the formula because we see we are compounding continuously. So that's how we know this is the right formula. And we want to know what is going to be this balance after 16 years. So we're going to plug in that starting amount, E, to our R value 2 times T, right? So in our calculators, we're going to just, again, type basically all that in. Starting value, and then second ln is going to give us E to the power, or you could have done just second division sign to get the E and then raise it yourself to the power, but 0.0289 times 16. And we see that you would have about $13,000 on that one. $13,619 and then 25 cents if we round to the nearest hundredth for the cents, right? The next example says we have Daniel, and Daniel is going to start by investing $4,409 in his retirement account. His R value, his rate is 2.93%. And again, we see that compounding continuously, so we know we're using this PERT formula. And we want to know what is the time it's going to take to get to our final amount here of $6,453.02. That is the final amount. So we're going to set that equal to our starting amount, E, times our R value, times T. So our goal is to get T by itself this time. So we have this coefficient out front, and we've talked about before, we're going to start this time by dividing that over. So if we take our amount, divide over that principal starting amount, we get about 1.463. Again, use a bunch of decimal places, and this time it equals E to the 0.0293t. Now we want to be able to get that exponent with our variable out front. And something that is going to undo our E is this ln value. Because if we take the ln, not of pi, ln of E, we're going to notice it basically cancels out, right? Ln, the natural log, we call that, cancels out with E, and it equals 1. So what we can do is take the natural log of both sides, because what happens is this cancels out. We're left with the ln of the 1.46 decimal, and that's going to now equal, since that canceled out, 0.0293 times T. So if we divide over that decimal, 0.0293, we'll get T by itself. So I could take ln of my 1.463, not ln twice, I only wanted that once. So ln once of the 1.463601 1.1724. And I'm going to divide that again by that rate, which was 0.0293. Not 2293. 293. And we see that that answer is right about 13. Okay, so our t value this time is right about 13 years. All right. Our next example has Carlos, and Carlos is investing $5,016 into his account, compounded continuously. After 15 years, we have a balance of over $13,000. What is the interest rate this time is our question. So this time we are going to take, again, that final amount and set it equal to our starting e to the r times t. So very similar to our last problem, we need to get one of those exponent values by itself. This time the r, not the t. So we're going to still start off by taking 13,723.82 and dividing over that principal value of 5,016. And again, this time we have 2.736, and we have all this equal to e to the r times t. And again, if we take the natural log of both sides, that cancels out our ln e, and we just have r times 15. So we can divide over the 15 from the ln. Again, we still do need the ln on the left-hand side. Divide over the 15 to get our r value by itself. This time r is going to equal about 0.0671, which if we move over our decimal place is about 6.71%. All right, last but not least, we have Jessica, who is investing a sum of money into a savings account. This time she has a rate on the account of 2.18%, compounded continuously, so we know we're using this formula. After 9 years is our time, and we know our final balance, and we want to work backwards to figure out what is our starting balance. What's that initial p-value? So this time, we are going to set this equal p times e to our r value, can convert to a decimal, times our t. Now, e, remember, is officially a number, right? E is a stored value of about 2.718, right? So we can take e to our r times t and get an actual number here, right? About 1.216. So what's happening then to get my p-value by itself, because this officially is a number, I was able to type into the calculator, I can now divide both sides by that value to get my final principal value. So I could take 10,331.60 and divide it by that 1.21 value. We get right at $8,491 as our principal. All right, now there are two for you to try on the next page. This time we have Jennifer. We are solving for how long it's going to take her to reach our amount. And then in the last example, we have Maria, and we want to figure out if she, what her initial investment would be in order to reach that $35,000 mark. Thanks everyone for watching. We will work more with the end of activity 4 in class.